For the thermodynamic analysis of gas turbines, and here in particular for the ideal Joule cycle, things are quite easy. This is due to the fact that all the transformations are undergone by a gas, which can be considered as an ideal gas. And for this reason, we don't really need tables or thermodynamic diagram. It's easy to solve and to calculate what's going on. So at least for now, I will highlight the assumptions that are necessary to develop each step of the reasoning, and we'll first consider the compression across the compressor between A and B, which is considered as adiabatic but also as reversible for this ideal cycle. So first thing we can do is apply the first principle of thermodynamics. Here we have an open system at steady state, so we can apply this first principle saying that the technical work exchange plus the heat exchange between the fluids and the external side of the system is equal to the change of specific enthalpy between inlet and outlet of the compressor. And because the compressor is adiabatic, we know that Q is equal to 0, so we have this technical work between A and B is directly equal to the specific enthalpy difference, and for this we need to have an adiabatic transformation. Then because we have an ideal gas doing this transformation, we have the variation of specific enthalpy, which is equal to Cp times the variation of temperature, so dH is equal to Cp dt, and when it's integrated between A and B, if we consider that we have constant thermophysical properties, and here in particular constant Cp, we can write that the technical work between A and B is equal to Cp times the difference of temperature between inlet and outlet of the compressor. Then we want to go a bit further because we want to express everything as a function of the input parameters that have been presented before. And here we don't really know the temperature of B at the outlet of the compressor. And so we want to express this temperature as a function of other input parameters. And for this we will use two things. First thing, the ideal gas law that states that the product PV is equal to R, the specific gas constant of the gas considered, times the absolute temperature, and also the fact that when we have an ideal gas with constant thermophysical properties, and here in particular gamma, the Laplace coefficient, and for the particular case of an adiabatic reversible transformation, we have P times V at the power gamma is equal to a constant. So here we can say that this expression in A is equal to the same expression in B. And so we can combine both of them, especially replacing the specific volume by a combination of RT over P, and then we can express this way the temperature in point B as a function of the temperature in A. Here delta is the ratio of pressure Pb over Pa, and at the power gamma minus 1 over gamma. So those are properties of the fluid, also inlet parameters, input parameters. And so now that Tb is expressed as a function of the other parameters, then the technical work of compression between A and B can be expressed as Cp times Ta times delta at the power gamma minus 1 over gamma minus 1, and here we can express this only as function of input parameters of our problem.